Here's an example of a trig sub question where we have 48 over x squared times the square root of x squared plus 16, and this is a definite integral. It's going from 3 to 4. So you have to recognize it as a trig sub, and know that there are 3 flavors of trig sub. If the radical shows up as a squared minus x squared, you let x equal a sine theta. Flip that around. If the radical comes up as x squared minus a squared, you let x equal a secant theta. We have neither one of these. We have the third option, if it's a plus in between. If you let x squared plus a squared is under the radical, then you let x equal a tan theta. And so we have x squared plus 16 squared in the flavor of x squared plus a squared. That makes a equal to 4. And we would let x equal 4 tan theta. This is going to drive everything. This substitution, bringing in trig when there is no trig at all in the beginning, will make this integral doable. It's going to take a lot of work, but in the end, you end up with an integral that you could actually execute. Okay, so x is equal to 4 tan theta. Now you need to figure out what you need to replace. So in the integral, we have a 48. No need to replace that. Leave that. But we have dx, x squared, and x squared plus 16. Those need to be replaced. If x is equal to 4 tan theta, dx is the derivative of that. Derivative of tangent, secant squared. So we have 4 secant squared theta, d theta. If x is equal to 4 tan theta, we're going to square that and get 16 tan squared theta. And then finally, when your radical is x squared plus 16, then what happens is letting x equal 4 tan theta will turn the radical into 4 sec theta. You can work out the mechanics of that algebra, but basically with each of these trig subs, the radical becomes something that you could just have memorized or on a cheat sheet. With this third trig sub, the radical becomes a sec theta. Okay, well, we're ready. Let's plug everything back in now. The 48 stays there. As far as the bounds, don't put any bounds on. And what we're going to have is replacing the dx. We can put a numerator. Is the 4 secant squared theta d theta. And the other things in the denominator. The 16 tan squared and the 4 secant theta. Alright, well, we could do some canceling. The 48 and the 16 leaves us with a 3. The 4's cancel. And then the secant theta from the bottom cancel with one of the 2 secants that are up top. Leaving you with 3 secant theta on top of tangent squared theta. Well, especially with the d theta there too. This is a problem. This is supposed to get better. Is it better? We can't immediately tell how to find an antiderivative. It isn't obvious that the derivative of one piece is the other piece. It's not like that at all. So we're kind of stuck at this point. We're supposed to get better, and we went from some place where we didn't know where to start, figured out there was trig sub, and we introduced this trig in. We brought it in. We're supposed to be able to integrate that, and we can't. So we reach this point where we're kind of at our last resort. When in doubt, basically, the idea is to switch everything into sine and cosine. Not that it's always going to work, but let's give it a shot. So secant theta, in terms of sine and cosine, is the reciprocal of cosine. And tangent squared is going to be sine squared over cosine squared. Fraction over a fraction, we multiply by the reciprocal. So we're going to have 1 over cosine times cosine squared over sine squared. And the cosine from the denominator is going to cancel with one of those 2 cosines that are up top and leave us with cosine on top of sine squared. But I'm going to write it in this way, where I have sine of theta quantity squared. Makes it a little more obvious what to do here. So remember this trig sub, we brought in this trig, and now we're at this place. And it's better than we were before. Where we're at before with the secant and tangent squared, we couldn't do anything. We couldn't do a u sub. It just wouldn't work out. Oh, but now you can, because the derivative of sine is cosine. If you let u be equal to sine, then du is cosine theta d theta. Your numerator is du. And your denominator is u squared. And don't think that's a log or anything like that. It's a power rule. We got to bring it up as a -2 and add 1 to the exponent. -1 is what -2 plus 1 is, divided by the same thing. And that simplifies it. U goes to the denominator. Negative, you can put it up top. It's -3 over u. And to go back, u is sine, so we're looking at -3 over sine theta. We have integrated. Now we need to figure out what to do next. We got two options, really. We could do a limit switch to change the 3 and the 4 into thetas, or we can do a reference triangle translation of thetas back into x. With 3 and 4, look at the substitution, we'll end up with some non-unit circle angles. If 3 is equal to 4 tan theta, tan theta is 3/4. We don't know what angle that is. So this isn't the way to go. If we had nice 45, 30, 60 multiple guys, we would go with limit switch. So instead, we need to go with the reference triangle. Let's go to a new page. Alright, so we had this original integral. We let x equal 4 tan theta. And through all the substituting and the canceling and another substitution, we ended up with this being equal to -3 over sine theta. And we need to convert that back into x. The way you convert back into x is to use this actual substitution here. If x is equal to 4 tan theta, solve for tan theta, and then you'll have instructions on how to build a reference triangle. See, tangent theta is opposite over adjacent. So build yourself a reference triangle, a right triangle, where you have the opposite as x, the adjacent is 4, and then the square root that originally started all this is going to be the third side. Let me just put in theta there. Sorry. Okay. All right, great. So then we know that sine theta is opposite over hypotenuse, SOHCAHTOA, and so it'll be x on top of rad x squared plus 16, replacing the sine of theta. But you can, multiply by the reciprocal and put that radical up top, and now we're ready to plug in those bounds of 4 and 3. And I'm a big fan of just replacing the x's with the the upper and the lower bound, and later figuring out what that is. So first step, let's put 4's in, and then let's put 3's in, and put a minus, right? Fundamental theorem of calculus. Evaluate at the upper limit minus evaluate at the lower limit. 16 plus 16, that's 32. 9 plus 16, that's 25. And those 3's, they can cancel out. It's a negative that makes it a plus. Well, the square root of 32, well, 16 goes into it, and so that becomes 4 root 2. And so the root of 25 is just a 5. And then with the 4 root 2 and the 4 from the denominator, you can cancel further for your final answer of, I like to write it when it's a negative first and then a positive. I like to flip it. It's the same thing. And so I'm going to write this final answer as 5 minus 3 root 2. Okay? All right. Any questions? Comment down below. Hopefully this was useful. It's a trig sub example from one of my students. Thank you.